In the first video, I'm going to explain how to use binary trees in their most simple form. What's a binary tree? It's a data structure which allows us to store and organize elements of any type, the same way a chained list would. Except that a chained list only has one following element. Here, you'll have two, right and left. Let me show you how a tree looks like schematically. So this is a tree, super pretty. You can see that it's organized in a strange manner. How is it sorted? It's simple. For each node, you'll have on the left all elements that are inferior to it. If I take any node to compare it to another, for example 2 compared to 4, 4 is greater than 2, so it's on the right. If I take 0, it's inferior to 2, so it's on the left. And if I take 1, it's smaller than 2. But superior or equal to the other one, so it's in the right place. That's how a binary tree is sorted. What's the point of using binary trees when it comes to a list? With the tree, the traversal is much faster. I'm going to transcribe my tree into the shape of a list, like here. See, same elements are sorted. Imagine, for example, that I'm looking for the 4. So the worst case scenario, I'm going to have to take 1, 2, 3, 4, 5, 6 paths. So I have to do 6 jumps to reach my 4. Whereas in my tree, I do 1, 2, 3. So half as many. This allows us to go faster. And it'll be very useful when you'll have to store a large amount of data. That's actually what databases use to store multiple elements together. Another case of binary tree usage is with certain types of parsers. You'll learn about that later. It's not today's topic. It'll allow us to store other things such as tokens. What does a binary tree look like in C? It looks like this. Here we have the complicated shape of the binary tree. Considering we have a parent 2, so we have a structure S_B tree, which is a node from the tree. It has a parent, the equivalent of previous in a double chained list, and has 2 children, right and left. And then data, to store data. How to traverse a tree? You've seen it is weirdly sorted. There are many techniques depending on what you want to do with them. Let me show you the diagram. The first type of traversal is the depth first order traversal, meaning we'll retrieve the sorted elements in the first case, knowing there are different variations. The most common type of traversal is I'm scanning through the right, I'm scanning myself, I'm scanning through the left, or the other way around, left, me, right. If we base our example on this tree, I'm starting on the first node. I'm going to the left, and again. Here I don't have a left side nor a right side, so I'll display myself 0. Going back up, displaying myself 1, going to the right, 1. Going back up, displaying myself 2, going to the right, 3. 3 as there's nothing on the left, and then I go back to the right and display 4. That's in order traversal. There's also the pre-order traversal, which looks like in order traversal, except here we display before. It would look like this: 2, 1, 0, 1, 3, 4. In the post-order traversal, we display after, but we're not going to do them all. The second case of traversal is the breadth first traversal. In this case, I'll read it myself. Then I'll read my children, then my children's children by level. It'll go something like this: 2, 1, 3, 0, 1, 4. It's a little different, a little more complicated to implement in C. In the case of an in-depth traversal, we use a DFS. Google it. For the breadth first traversal, we use a BFS. You can Google it too if you're curious. So that's how you do traversal. One of the binary tree's disadvantage compared to list is that the insertion is more complicated. Here, if you want to add elements, it's a bit tricky. So we use what's called dichotomy. It consists of testing a value. Example, the first one you come across in the tree, let's say you want to insert -1. Here you'll check whether -1 is smaller. It is, so you go on the left. Check if -1 is still smaller. It is, going on the left. In the case here too, so you'll add a -1 here. So it'll be left of child of 0. Now let's imagine you want to add a 1 or another 0. You'll check if 0 is smaller than 2. Yes, so you're going to go on the left of 1. Check if 0 is smaller than 1. Yes, you go here. Here it's superior or equal, so you'll add it on the right. And you've just done an insertion in a tree. This type of binary tree isn't necessarily adapted to all cases. Imagine I inserted all my elements in a certain order and end up with something like this. I've inserted 10, then 9, then 8, then 7, then 6. My 10 is an element on the left, but none on the right. Same for the 9, etc. to infinity. It looks more like a comb than a tree. So we look at the speed and waste memory by having 2 nodes every time when we only use 1. In the next video, I'll show you how to solve this problem.